Have you ever stopped to wonder what carves out a riverbed? Or, what really keeps a massive jumbo jet hanging up in the sky? Or what dictates the weather every single day? Well, the answer is this invisible architect that's literally all around us. Fluids. Air, water, gases. They all follow a hidden set of rules. And today, we're going to pull back the curtain on the science that describes this beautiful chaos. Fluid dynamics.
And it is no exaggeration at all to say that fluid dynamics is one of the most fundamental forces shaping our world, and definitely our technology. You see it everywhere, from the grandest scales of nature down to the tiniest, most intricate machines. The principles of flow are always at play. Let's just look at a few quick examples. All right, first up, picture the air flowing over an airplane's wing. This isn't just some random wind, right? It's a super carefully engineered dance between a solid object and a gas, all governed by pressure and velocity to create lift. Or how about the water swirling around a river bend? The way it just carves away one bank and drops sediment on the other. That's a perfect natural display of momentum and energy transfer happening inside a liquid. And if we zoom way out, those massive wind patterns that create our weather, well, that's just a giant global-scale fluid dynamics problem, driven by things like temperature and the Earth's spin.
And then let's bring it back down to engineering. That invisible force of air resistance, what we call drag, that's the #1 enemy of a high-performance car. And trying to minimize it, that is a pure fluid dynamics challenge.
So you see the connection, right? All of these things, they're all connected. They're like different dialects of the very same physical language. But what exactly are the rules of that language? Okay, so this isn't magic, not even close. It's a whole field of physics with a really systematic way of understanding how fluids behave. So let's unpack the core rules that govern all this incredible motion.
Officially, we're talking about fluid dynamics. It's the branch of physics that's totally dedicated to describing the flow of pretty much everything from air to water. And the goal is to be able to calculate key things, like velocity and pressure at any point in the flow, at any given moment.
But how in the world do scientists even begin to tackle a problem that complex? Well, instead of trying to analyze an entire ocean at once, they do something really clever. They isolate a small, finite region of the flow, what's called a control volume, just like you see here. By focusing on this one manageable piece of the puzzle, they can apply fundamental physical laws to understand the whole big picture. And you know what's amazing? Those fundamental laws are actually ones you've probably heard of. At its heart, all of fluid dynamics really just rests on 3 main pillars. First, the conservation of mass. Basically, you can't create or destroy stuff. Second, Newton's second law, F equals ma. And third, the conservation of energy. It just changes form. That's it. So these 3 principles get translated into what are known as the governing equations. Now, you might have heard of the most famous of these, the Navier-Stokes equations. But try not to think of them as just scary, complex math. Think of them more like the precise, universal language that describes how every single fluid moves.
All right, now that we have the rules, let's look at the 2 main ways fluids actually play the game. Turns out, every flow you have ever seen falls into one of 2 fundamental states. Either it's smooth or it's chaotic.
And this shows the difference perfectly. On one side, you've got laminar flow. It's smooth, it's orderly, kind of like layers of a cake just sliding past each other, nice and neat. Then, on the other side, you've got turbulent flow, and that's the chaotic, messy stuff, full of swirls and eddies. Honestly, most of the flows we see every day, like water blasting from a faucet, are turbulent.
So how can we predict which state a flow is going to be in? Well, the secret is a special value called the Reynolds number. It's just a simple ratio, really. It compares a fluid's tendency to keep moving, its inertia, against its own internal friction, or its stickiness, which we call viscosity. If the Reynolds number is low, viscosity wins, and the flow is smooth and laminar. If it's high, inertia takes over, and things get turbulent.
Now, let's zoom in on where these forces really duke it out. Right up against any solid surface, there's this super important zone called the boundary layer. Because of that stickiness, the fluid right at the surface actually sticks to it. It doesn't move. We call that the no-slip condition. So in this tiny thin layer, the fluid speed has to ramp up from 0 all the way to the full speed of the surrounding flow. This is where all the action really happens.
And believe me, the state of this boundary layer changes everything. A laminar boundary layer, as you can see, is thin and smooth, and that creates less drag. But a turbulent boundary layer, it gets thicker, way more chaotic, and it generates much higher wall stress, which, you guessed it, means a lot more drag. So the takeaway here is that controlling this tiny little layer is absolutely crucial for any kind of engineering design.
And that brings us to the big payoff. I mean, why do we study all this stuff? It's because when we understand and predict flow, we can actually harness it. And that completely transforms what's possible in the world of engineering.
The applications are just everywhere. I'm talking about designing quieter, more fuel-efficient planes and cars, creating better wind turbines, predicting the weather, managing huge water networks, and even designing ships. All of these fields rely on mastering fluid dynamics. Just take aerodynamics, for instance. The entire goal of designing a wing is really to manipulate that boundary layer. Engineers will shape the wing to keep the flow attached to the surface, trying to delay that transition to turbulence for as long as they can to ultimately minimize drag and maximize that all-important lift.
So what they're doing is managing the two key forces you see right here. They use those big governing equations to figure out the pressure, that's the P, which is the force that pushes on the surface, and they calculate the shear stress, that's the Greek letter tau, which is basically the friction of the fluid rubbing along the surface. Getting the balance between those two just right, that's the very definition of performance and efficiency. So, have we figured it all out? Not even close. Fluid dynamics isn't some solved problem sitting in a textbook. It is one of the most active and challenging frontiers in all of science.
And the biggest reason why is turbulence. While we can describe it, fully predicting its chaotic, swirling nature, from a massive hurricane down to the tiniest little eddy in a stream, that remains one of the last great unsolved problems of classical physics. It's this beautiful, incredibly complex puzzle that we still haven't completely cracked. And this is where our modern tech comes into the picture. To tackle this massive challenge, we rely on a tool called computational fluid dynamics, or CFD. We use the most powerful supercomputers on the planet to simulate those governing equations, which lets us get closer and closer to predicting the beautiful chaos of real-world turbulent flows.
And that leaves us with a really fascinating question for the future. I mean, think about it. We've gone from just watching flow in rivers to designing supersonic jets. So as our ability to simulate and predict how fluids behave gets even more powerful, what incredible new things are we going to build next?